Most people are here. Let's a little bit out. There we go. What we're looking at today is finishing off section 3.6, and in particular, seems to be nudged a bit more. There we go. In particular, what we're going to do for the first part of today, most of today, in fact, is we're going to look at the derivatives of the inverse trig functions. But before I do that, let's give you a little recap of some of the derivatives we already know, and then I'm adding the extra ones. Remember, we found the derivative of things like 2 to the x and 4 to the x, and its derivative was this guy. You notice I had the extra log, natural log of 4. If you take log of x, its derivative is 1 over x. Here's the new guy. If you want to differentiate the log to a different base, right, log to base 3 or log to base 10, for instance, right? If you want to differentiate that, excuse me, the answer still is a 1 over x, right? But do you see it's got an extra, not multiply now, but essentially divide. Excuse me. One of the mistakes people make, because these two processes look so similar, is that they forget that when it's a 4 to the x, you multiply by the log. When it's a log to the base 4 or whatever, in this case 3, you divide by it. So that's just something you have to memorize. Here are 3 new guys, the guys we're going to be spending the beginning of today on. The derivative of the inverse sine function. The inverse sine function, oops, got some people coming in. The inverse sine function is from 142. Remember when you were solving triangles, you take the inverse sine of both sides, that kind of thing. Right? And you may actually have sketched it, but probably quite superficially on a calculator, what the inverse sine. So that does not mean -1 power, right? It's notation that just means inverse sine. And its derivative has nothing to do with sines. You might have thought that the derivative of the inverse sine was, I don't know, the inverse cosine, or a cosine, or something trig-ish, right? There is such a word as trig-ish. But look at its derivative. Now, I won't prove that, but if you want to see a proof, you can. They use implicit differentiation. Just have got a time issue, so it's going to be a bit of magic. You're just going to remember it. Right, when I want to differentiate an inverse sine, this is the guy you get. When I want to do an inverse cosine, this is the guy I get. When I want to do an inverse tan, this is the guy I get. If I wanted to do an inverse cotangent, cosecant, or secant, I would just go looking the thing up, because nobody expects you to memorize those ones. So, we're going to look at differentiating functions that contain inverse trig functions. Excuse me. So, product rule, quotient rule, chain rule. Let's do x squared, the inverse sine of x. Let's do a nice simple one to start with. I would like to differentiate this function. It's essentially 2 things multiplied, so this is going to be a product rule. F dash g plus f of g dash. If you differentiate x squared, you get 2x, you leave the other guy alone. You leave the f alone, and you differentiate the inverse sine, and you get 1 over the square root of 1 minus x squared. There's really nothing that you can do on this question, at least, with style points. So that's basically the end of the question. Okay, so that would be a pretty simple, relatively straightforward sine rule. Okay, inverse sine product. How about a quotient then? How about 1 minus x squared Well, let's change that. Let's do inverse sine on the top. That's better. And do a 1 minus x squared on the bottom. Now, if I wanted to do this fella, it'd be a quotient rule. So it'd be f dash g, take away f g dashed over g squared. If you differentiate this guy, you get very ugly, that fella, times g, take away inverse sine of x, and if you differentiate that, you get negative 2x, and the whole thing is over 1 minus x squared squared. Okay, this one's not anywhere near as simple as the earlier one. A 1 minus x squared multiplied by a 1 over the square root of 1 minus x squared. That cancels, doesn't it? And what you got left is the square root of 1 minus x squared. Take away makes it an add, 2x, inverse sine of x, all over 1 minus x squared squared. You agree that's a little bit more convoluted than the product rule, but it's still a quotient rule, right? Are we cool with that? F dash G and all the pieces that go in to make it. So let's do a nice simple chain rule. How about the sine of the inverse cosine of x? Right. It's a sine of something, right? It's not a multiplication, right? There's not a sine x times this guy, right? It is a distinct sine of something. It's a chain rule. So if you want to get its derivative, the sine of something is the cosine of something times the derivative of that something, which is negative 1 over that guy. And now I want to make this fella pretty. You have to remember a way back to 141. Actually, 142 does it as well. What do you get if you take the cosine of an inverse cosine? What does that simplify down to? Any takers? The cosine of the inverse cosine of x, what does that get you? A function and its inverse working together. Last chance?
Is it just x?
Yes, it's just x. And that's that one finished. Do you know, like the square root of something squared just gets you x, right? The log of e to the x just gets you x. There are examples of that process. So the sine of an inverse cosine or the inverse cosine of a cosine, those essentially cancel each other out and you're left with whatever is there. So that was a product rule, a quotient rule, and a chain rule. But they were relatively nice ones, right? There wasn't too much going on. So I'm now going to go and do a product, a quotient, and a chain rule, but they're going to be much uglier, right? So if you bear with me, I'm just scanning to see if I can find a decent one. That's a little bit easy. Yes, still too nice. Let's do, oh, this one, yes, definitely. This one's cool. This one is a question 24, or at least it's like it. And you've got a function, the square root of 1 minus x squared, take away x the inverse cosine of x. Now I'm going to rewrite this as 1 minus x squared to the half. So essentially, there are two things happening here, right? I've got to differentiate this guy, and I'm going to do the product rule on this guy. And since I'm going to do the product rule on this guy, let's call the whole thing, including the negative, the f, and this guy g. And by doing that, I don't need to worry about the sign of the answer. It'll be part of the answer. I won't need to compensate, you know, get the answer and then subtract it and all that thing. So calling that negative x is going to save me. This here is a chain rule. So it's a something to the half, gets you a half, something to the power of negative half, times the derivative of that something. And those two cancel. You've got an x and a negative. So when I'm finished, are you okay with the derivative of this becoming that? Yeah, you okay with the derivative of this becoming that? Are we good? Okay, product rule. F dash g plus f of g dash. I can do a plus here because I'm using that as a negative f. So what do I get? I got negative 1 times leave that guy alone. Technically plus this fella over the square root of 1 minus x squared. And I need to work on this guy. That's good. There. The derivative of the inverse cosine is negative 1 over that. Almost missed that. So I have negative x over this ugly square root minus an inverse cosine of x. These two give you plus x over an equally ugly guy. And then, oh, they cancel. There's our answer. It's actually quite a nice answer. Nicer than I thought. Are we good? Any questions about that before I move on? Well, I guess I'll put it there. Let's do a ugly chain rule, quotient rule guy. So the fill I'm going to do now is going to be 25. You should be afraid. You should be very afraid of this guy. Just looking at it, can you see this one is fraught with danger? There's a lot going on. It's the inverse tan of the square root of a fraction. So as far as chain rules go, isn't this like a Russian doll, right? It's a chain rule inside a chain rule inside a chain rule. If that wasn't bad enough, it's an inverse tan, so we've got to cope with that. And if that wasn't bad enough, don't we have to do a quotient rule because of this piece? And added on top of all of that hard work, we still have style points to deal with. So when I get something that's really messy, one of my strategies is to take it slow and take it in little manageable chunks. So this is the inverse tan of something. The derivative of the inverse tan of something is 1 over the something squared plus 1. Here is the something squared plus 1, followed by the derivative of that something. And as I said, take things slowly. So I am going to take this ugly thing and see if I can make it nicer. So this is like my working on the side. Right, if you take this guy and you square him, well, if you square a square root, you basically cancel out the square root, right? Now that guy ain't going to cut it. We do not like fractions with fractions in them. I don't like this 1 minus x, so let's see if I can make it pretty. So I'm doing style points here. What special version of 1 do you think will fix this fraction problem? What special version of 1 would I multiply by? Running short of time. Anybody?
I want to say 1 minus x, but
You are right. That's exactly what you use. And if that was x squared, wouldn't I multiply top and bottom by x squared, right? And if it was some weird stuff, wouldn't I multiply top and bottom by the weird stuff, right? Essentially, that's how you get rid of this fraction. Now, 1 times the top is 1 minus x. Yeah. This guy times this guy gets you 1 plus x. Added to this guy times this guy gets you 1 minus x. I have 1 minus x on the top. Oh, they cancel and you get 2. So I guess my answer is that, oh, it was nice. Do you see what style points has done? Is it's taken something that you would just go, ugh, and it's actually simplifies just to a half 1 minus x. That was good. Right, let's look at the derivative guy. The derivative of this fella. Okay, if I want to find the derivative of a square root, shouldn't I really call it a half power? Okay, so, oh, another chain rule. Something to the power of half. The derivative is 1/2 something to the power of negative a half times the derivative of that something, which is this guy. And so I'm now going to want to try and fix this fella. I have a half 1 plus x over 1 minus x to negative a half. And I want to see if I can make it a little bit prettier. Well, I could do something like this. Oops. Can you see what I've just done to take this negative a half power and turn it into a positive a half power? Because negative half powers are not very pretty. Do you notice I've taken the reciprocal? And what I'm going to do now, not too much. I'm going to call it that guy over that guy. And I'll leave it like that. So I've got times 1 minus x to the half power all over 2 1 plus x to the half power times the derivative of this guy. It's slowly unraveling, right? Can you see each time I do it, I get a little bit better, right? A little bit closer to finishing, right? If you want to find the derivative of this, won't we just use a quotient rule? So f dash j, take away f of g dashed over g squared. Top guy's derivative is 1. Leave the bottom guy alone. Take away. Leave the top guy alone and differentiate the bottom guy. All over 1 minus x squared. 1 times that guy gives you this. Negative negative makes that a plus, so you essentially get this all over that guy. Oh, and some nice things happened. So I have, well, let's do some tidying up. Do you know this guy and this guy can be combined? So what do I have now? I have a half, 1 minus x to the 3 halves. Oh, that basically a half and this guy is a quarter. Let me rewrite that slightly better. 1 minus x to the 3 halves. That's 4 on the bottom and a 1 plus x to the half. So all I've done there is tidy this up a little bit. And this fella we just got a few seconds ago. This guy here is 2 over 1 minus x squared. We're pretty much at the tail end of this answer. Can you see, whoops, can you see this 2 cancels with that 4 and leaves a 2? What's going to happen when this 1 minus x to the power of 3 halves cancels out this 1 minus x squared? What's going to be left?
1 minus x to the half power on the bottom.
Would you agree this is getting nicer? Every time a little bit nicer. Keep going till you can't see anything else to do. I can still see some things that I can do. Remember, style points says that things should look like the original. Didn't the original have square roots in it? So I'm going to call this 2 the square root of 1 plus x multiplied by the square root of 1 minus x. Keep going till you can't do anything else. Any suggestions for what I could do next, even if it's minor? What could you do with these 2 square roots?
Combine them in FOIL.
Okay. So if you combine them, they look like that. And if you FOIL them, they look like that. Now, considering what that question looked like, is it not a remarkably nice derivative? Convert them to square roots, multiply them together. Oh. That's the worst question in the homework, so I've kind of done most of it for you. Last chance, any questions? So what have we learned today? Hopefully that you can differentiate 3 more guys. So if you were doing a hit list of what function should I know the derivatives of, every polynomial in the universe, right? 5x cubed and stuff. All 6 trig ratios, right? Sines and tans and cosines. E to the x, 4 to the x, log x, log to the base 3x, and lastly, the 3 inverse trig functions. That's a pretty decent list. In fact, as far as you're concerned, it's the end of the list. There aren't going to be any more new functions added to your repertoire of things we can differentiate. So at least you know that there's a finite number of them, at least that you need to worry about right now. I'm going to call that good. if we have any other questions. Right. Let's do our next section then. At least start. But it's going to feel like a kinematics class. I think it's physics or kinematics. You've done this. When you use a term like rate of change, I want you to think it's equivalent to saying derivative. So if I went and said to you, for instance, the rate of change of position with time, what do you call that thing in physics or kinematics? What's the rate of change of position with time?
Velocity?
Correct. What is the rate of change of velocity with time?
Acceleration.
Acceleration. So how does calculus help us find velocities and accelerations? Well, imagine I have a function that tells me the position of an object at any given time t. If I want to find the velocity of this moving object at any given time t, we'll call that the velocity function. You just differentiate position function. And if I wanted to know what the velocity of this moving object was at any given time, let's suppose I'd like to know what its velocity was at the 1 second mark, it would just be 2 lots of 1 plus a 2, take away 3 lots of 1 squared, and the answer would be 1 meter per second. And of course, if I wanted to know what its velocity was at the 2 second mark, it'd be 2 times 2 plus 2, take away 3 lots of 2 squared, which I believe is -6 meters per second. Now, for those people who have not taken physics or kinematics, you might be a little bit surprised by the fact that you can have negative velocities as well as positive velocities. But if you have taken those classes, aren't you quite comfortable now that velocity can be negative as well as positive? And if you want an analogy, can you imagine that this position function is actually its height at a given time? Then a positive 1 just means it's going up the way at 1 meter per second. And a -6 means it's hurtling towards the ground at 6 meters per second, right? So there is a direction to velocity. Up and down is a good analogy. When you don't have up and down, it tends to be left and right. You know, left is negative and right is positive typically. So if you find the derivative of a position function, you will get its velocity. If you find the derivative of the velocity function, you get its acceleration. Now, if the velocity is the derivative of the position function, then isn't the second derivative of the position function the same thing as the first derivative of the velocity function, which is the same thing as acceleration? In other words, first derivatives get you velocity and second derivatives get you acceleration. Isn't that cool? That you can use calculus to find velocity and acceleration of any moving object, provided you are told its position function, right? Where it is at any given time. So in this question here, I know that its velocity is 2t plus 2 take away 3t squared. I can also find its acceleration, because that's 2 minus 6t. And I guess for completeness sake, I'll put the position function at the top. Now, what that tells us is that if you know where an object is at any given point in time, that's what its position function does. If you know that, don't you know its velocity and its acceleration? Right? You can calculate them using calculus. So rates of change, any rate of change, could be, if I know the temperature of an object at any given time, then the rate of change there, right, would be its derivative. If I know the cost of an item at any given production level X, then I can find its rate of change of that price by just finding its derivative. So I want you to think, when you see the word rate of change, to think, we're differentiating something. And you just need to find out what that something happens to be. Here it's position, but it could be anything at all. So if I went and said the cost function, when you produce X items, is 7x squared minus 4. If I wanted to know the rate of change of the cost function, it's that guy. And very often, the things that are rates of change of things have names, like velocity or acceleration. I believe this one's called the marginal cost. So if you're into business, finding derivatives are really just finding rates of change. So how are things changing? You know, how is the price going up or down at any given point in time? Right, that's a rate of change. Right, something's changing. Pretty cool. For completeness sake, because I told the other class, and I feel I have to tell as much as I can remember the same things. Do you know that if you differentiate the acceleration function, you are getting the rate of change of acceleration, right, with time? I know that first derivatives are called velocity, right, because that's very common, right? Rate of change of position with time is velocity. The rate of change of velocity with time is called acceleration. But here's the $1 million first prize. The rate of change of acceleration with time is called something. Has anybody ever came across it in kinematics or just anywhere? What the rate of change?
It's called jerk.
It is, Sabrina. No, it's true. I was told by a student, Sabrina, you can tell me that that's really not the case, but it will do, that if you are in a moving object and the acceleration is a constant number, right? The acceleration is 10 meters per second squared or something. If you're in that moving object, you really don't notice the increase in velocity because it's reasonably smooth, right? Although you're accelerating, because you're accelerating by the same amount, it's pretty smooth. But if you're in a moving object where the rate of acceleration is itself changing, right? It's going from 2 to 5 to 7 to 9, right? What you would physically feel would be a kind of jerking motion as it kept on changing. And that's probably where the name came from, right? Does that seem like a reasonable? You seems reasonable? Right. Just because I'm nosy, because not many students know that name, where did you hear it?
I was just doing a deep dive into how far you could go with some of these. Well, I was studying earlier, like
cool.
a couple weeks ago.
Right. Yeah, I'm just curious because some the student I got was in Submariner, and evidently when you're a Submariner, you get to go to all sorts of courses, and he was told that at one of his courses. So maybe it's something to do with the engine, you know, the nuclear engine when it changes and, you know, goes slow to really fast, really quickly, that there's probably jerk involved in that process. Oh, kind of interesting, isn't it? I believe that there's other names after that, but they're less used and I can't remember them off the top of my head. But velocity and acceleration are the ones that we are going to deal with. So let me set up a pretend story. Let's have an object being thrown into the air. And over an 8-second time period, that's what its position time function would look like. So it's basically, you know, if you get a rock and you chuck it in the air, it goes, right? And I'm going to find velocity and acceleration of that moving object. And I've kept the numbers nice and simple. The velocity at any given time t is 8 take away 2t, right? The derivative. And the acceleration at time t is even easier. Would you agree in this case it's -2? So this would have to be a rock thrown on Mars. Because if this was a rock thrown on Earth, wouldn't that number be a number that you've seen? And what would that number be if you go metric? Does anybody remember what gravity's constant is?
9.81 meters per second.
Yeah, negative because it's, you know, pulling you down. So on Mars, this is what we've got. So if I wanted to know the velocity of this object at the 2-second mark or the 4-second mark or the 8-second mark, couldn't I just plug in 1, 4, and 8? If I wanted to know the acceleration, it wouldn't really matter. Wouldn't it be -2 no matter what the time was? If I wanted to know its position, wouldn't I be able to plug in 1, 2, you know, anything up to 8 would make sense. But I'm going to find that guy. And at that point there, won't the tangent line be horizontal? And horizontal tangent lines are 0 slope. So doesn't that mean that theoretically, when a rock is at the highest point that it goes, for an instant in time, isn't it essentially stationary? 0 velocity. So let's find where that guy is. So I'm going to solve when is the velocity 0. And you could tell by my picture what the answer is going to be. But just for math purposes, does 4 seconds seem really reasonable? I mean, just looking at the symmetry, doesn't that make sense? But here's something that's not so obvious. This object's going to hit the ground at the 8-second mark. I can see in my picture it is. I would like to know what the velocity of that rock is when it hits the ground. Well, the velocity at the 8-second mark, because it's 8 seconds, is 8 take away 2 lots of 8. It's -8 meters per second. So at that point there, the rock is heading towards the ground at 8 meters per second. Do you see that because I know the position of the object, don't I know everything that I could possibly want to know about this moving object? Right, with a little bit of algebra, couldn't I find its velocity and its acceleration at any point? Couldn't I even find out when the, at what time its velocity is 0 or -2 or +5? Can't I find when its velocity when it hits the ground? A much more sophisticated version of what's going on here is typically done. It's done in 3D, so you'll have to wait to Calc 3 to find out how to do it in 3D, but it's not that dissimilar to what we've got. And let's say they see an asteroid out in deep space and they've detected it. And one of the things that they do with asteroids, especially new ones, that they don't know what their path looks like, don't they tend to put a little bit more special attention because they don't want them to hit the Earth, right? Asteroids hitting the Earth tend to be bad news. Ask the dinosaurs, right? Not good if a big one hits. So they watch it. And what they do is that they find its position in 3D space. It's not that difficult, you can do it through observation. And you collect as many data points as you can. And then you put it into a computer and you basically say to the computer, create a position function for me. Now, once you've got that position function sorted out, can't you then say, this is the path that asteroid's going to take. And this is the path the Earth is going to take. Let's see if they keep away from each other. And if they do, you say, fine, that asteroid's not that interesting. We'll just put it in our database so that the next time it comes around, we know it's safe or whatever. But if it's a bad one, don't you want to know that asteroid might be coming towards us? And occasionally, don't you get, there's a near, well, they don't call them near misses, but there's a near asteroid, right? An asteroid that's going to get near to the Earth. And I was saying to the other class, they used to scare me sometimes. Do you know how near you need to be even recognized? You need to be somewhere between the sun and the Earth. Do you know how big that space is? You're totally safe. Do you know what a near asteroid, one that's really close? Anything that comes between the moon and the Earth. So any asteroid is in that space between where the moon is and where the Earth is called a near. A near, don't stick the word miss on it. But you know that's 250,000 miles. Okay, imagine asteroids the size of a car, which is considered dangerous, because asteroids that size might actually make it through the atmosphere, right? So you get an asteroid the size of a car, they're kind of interested in that. Imagine something the size of a car has got 250,000 miles to miss the Earth. We're kind of safe. Would you agree that we don't get hit that often? But if we ever did get hit, at least we'd have the calculus to tell us what velocity it was going to hit us with. Because if you know anything about damage, there are two things that causes damage. It's not just the mass of an object. Do you know if you had a really 200-ton object and it was moving at half an inch an hour, and you were standing there when it hit you, you wouldn't get hurt, would you? You'd probably feel a small bump, because speed, right, velocity, is part of the equation. Can't a small object that weighs an ounce traveling 1,000 miles an hour do a lot of damage to you if it bumped into you? Couldn't 1,000-ton moving at a really slow speed do no damage to you? So don't you want to know the velocity of that asteroid as well as its size? And since you know the position, you've got everything. So the one last thing I want to talk to you about. So while I'm doing this, you can say hi so you don't forget. And I am slowly finding the darn thing by closing lots of other windows first. That window gets closed. That looks good. That looks good. Boom. Almost there. Almost there. That goes here. Student view. Home. Where the heck is that? Where'd you go? Excuse me. Something disappeared. It's not meant to disappear. I want to show you. Okay. I'm going to have to show you something else which is identical to yours. And then once I've finished, I'm going to go in and figure out why I can't do it. All right, okay. This is important news. Make it a little bit bigger. Right. If you go in about 10 minutes from now to our class Canvas site, you'll see a guy called 2% extra credit, and it's due midnight on Sunday. So I thought you could see it right now, but evidently I forgot to put the publish button on it. So I'll go in and fix that in a minute or two. If you click on this guy, you will see, and I'm assuming, can you see what I can see? Do you see a video? Right. There will be no class on Friday. Instead, there will be this virtual class. So it's a virtual class inside a virtual class. So I would suggest that you just turn up and watch this video as if it was our class. That would be the easiest way to do it. If you watch this video, you will get 2% of your grade, and you have to do something. Inside this video, there are 5 questions, and you will do these questions, and you will write the answer by hitting that guy up there. I have no idea what that is, but I'll say yes. Right. There we go. You have got that guy there, and you type in your answers. Question 1 is this. Question 4 is that. Click down here. Question 5 might be a decimal. It's not, but it might be. And that will be my proof that you actually did watch the video. So you will look at them and you'll just be watching the video, and I'll be showing you a concept. And this is, instead of teaching you, called linear approximations and differentials. So this is from section 310. So if you watch this video, we'll have covered 310. And I do examples. And then I give you a question like it. And I do an example or two, and then I give you a question like it. So as you go through the video, you can do it any way you like, but I would probably pause it and do question 1, because I've already shown you a version of how to do it, and then you could kind of repeat that process. And you'll be done. And then submit assignment when you're happy with your answers. I only need to see the answers, although there'll be quite a few bits and pieces of working. And that's it. Any questions? Now, it is a 2% extra credit, so everybody who does it gets 2% added on to their extra credit column. That could be important to some of you. You do not want to be a 1.8 and kick yourself for not doing this, because that extra 2 could make you a 2.0 and you pass. And you don't want to be a 3.8 person at the end of all of this and kick yourself because you could have been a 4.0. So there's one reason. And the other reason is that's the only way you're going to find out how to do linear approximations and differentials, because I'm not going to be teaching it, because I've essentially done it, right? So any questions? We're pretty much finished. Okay then, if there are no more questions, you've already said hi.